These examples go with section 7.1, confidence intervals for a population mean, standard deviation known. This is part 2 of the examples. Here's example 8. We're going to construct a 98% confidence interval for the mean lifetime for the battery in example 5. Now we'll go back here and we'll look at example 5 so you can remember what the problem was. The lifetime of a certain battery is known to be normally distributed with a standard deviation sigma equals 20 hours. A sample of 50 batteries had a mean lifetime of 120.1 hours, and it is desired to construct, now this time we're looking for a 98% confidence interval rather than a 95% confidence interval. Okay, so over here, I've written down our important points here. We've got the 120.1 hours, our sigma, and the number of items in our sample here. Okay, so let's go through the same process we were before for constructing a confidence interval. The first one thing we want to know is, what is our point estimate? Well, that's just going to be our mean, and it's our point estimate because that's what we're constructing the confidence interval for. So we got 120.1. All right. The next thing we want to do is find out what the critical value is. Now remember, the critical value comes off of table A3, and we're going to be looking down on the Z line, and we're looking at 98%. So we're looking for the critical value on the Z line that goes with 98%. So let's pull up table A3. And we want to go down to the Z line. Hold on a second. There we go. And the Z line right down here, we're looking for 98%. There it is. And the critical value right above it, 2.326. Okay. The next thing we're supposed to do is calculate our standard error. Well, let's remember our formula for standard error. That's the standard deviation divided by the square root of our sample size. And in our case, we're looking at 20 divided by the square root of 50. Now, we've already calculated this once before, but I'm going to put it again in my calculator because I lost the data there. And I am looking at two times the square root of 2, which is going to give us about 2.828. 2.8284 as a matter of fact. Okay. 2.8284. Okay. Then we're supposed to calculate the margin of error. This is going to tell us how far we need to go to the left and to the right of the point estimate to be, in this case, 98% confident that the true mean falls within our range. All right, the margin of error, and again, let's review the formula. That's just going to be the standard error, which we just found, times the critical value, which we also just found. So we're looking at 2.8284. And we are going to multiply that by 2.326, and then we're going to round that off to 4 decimal places there. Okay, 2.8284 times 2.326. And this is giving me 6.5789. 6.5789. All right. Now we're ready to figure out what our confidence interval is going to be. The confidence interval, the formula for that, remember, was to take our point estimate and we're going to subtract off the margin of error. That's going to be the lowest end of our confidence interval. And then we're going to take our point estimate and we're going to add the margin of error. And this is going to be the upper end of our point estimate. And This one, the mean was rounded to 1 decimal place, so when I give my final answer, it's going to be rounded to 1 decimal place as well. All right, so let's see, we got 120.1, and we're going to subtract off that margin of error, 6.5789, and then we're going to take the 120.1, and we're going to add 6.5789. Let's see what we get. The first one is going to give me 113.5211. Well, if we round that to 1 decimal place, that's going to be 113.5. That's going to be my lower end. For the other one, I get 127.2789, and that's not right because I just put the wrong thing in there. Hold on, 120.1, it's 126.6789, and if I round that to 1 decimal place, that's going to give me 126.7, and that's because the 7 right here is going to round that 6 up to a 7, but the 2 does not round the 5 up to a 6. All right, and there's our confidence interval. We are 98% confident that the true population mean is between 113.5 hours and 126.7 hours. Example 9. To determine how well a new method of teaching vocabulary is working in a certain elementary school, education researchers plan to give a vocabulary test to a sample of 100 sixth graders. It is known that the scores on this test have a standard deviation of 8. The researchers plan to compute the sample mean x-bar and then construct a 95% confidence interval for the population mean test score. Question A, what is the critical value z sub alpha over 2 for this confidence interval? We are looking for the critical value for a 95% confidence interval. We're going to pull this off of table A3. Down on the z line, 95%, it goes with 1.960, the critical value, 1.960. Now it's asking to find the margin of error for this confidence interval. Okay, so we're going to have to squish a couple of steps together into one process, because remember, the margin of error is supposed to be my standard error times my critical value. Now the critical value I've got, but the standard error I don't. The standard error formula was to take the standard deviation and divide it by the square root of n. Alright, so if I'm going to do this all in one step, then my formula becomes the margin of error is the standard deviation divided by the square root of n times my critical value. So I can just mash these two formulas together and create a brand new one, and it'll take me straight to the margin of error there, and I can skip a step when I'm trying to do my problem. I don't have to go through every single one of these one by one by one. All right. That means our margin of error is going to be the sigma, which they told me right here is 8, divided by the square root of n, our sample size, 100, they gave it to me right here. And this is going to be multiplied by 1.960, which is the critical value we just now found. So let's put this in the calculator and see what happens. This is giving me 1.568. 1.568. Okay, question C, let M represent the margin of error for this confidence interval. For what percentage of all samples will the confidence interval x bar plus or minus M, that's our point estimate, plus the margin of error and minus the margin of error, cover the true population mean? So what percent will that confidence interval cover the true population mean? And fortunately for us, that's given to us right here in the problem. If we're 95% confident, then the true mean should appear in our interval 95% of the time. If we did this, if we took a sample over and over and over and over again, okay, of 100 sixth graders, take 100 one time, find the mean, then take another sample of 100 sixth graders, find the mean, take another sample of 100 sixth graders, find the mean. If we did that 100 times, then we would expect that 95 out of those 100 times, our confidence interval would actually contain the actual population mean. And that's where the 95% comes from. This is how confident we want to be right here. Example 10, the researchers now plan to construct a 99% confidence interval for the test scores described in the previous example. What is the critical value z sub alpha over 2 for this confidence interval? We're going to find the critical value in table A3. We're going to look up 99%, and the critical value should be right above it. Okay, 99%. Here it is, 2.576. That is the critical value that we're going to use. B is asking us to find the margin of error for this confidence level or confidence interval. Now we just changed our margin of error formula and said we can do the standard error formula times our critical value all at one time instead of having to do it in two separate steps. All right, our sigma, I think that was 8. Yes. That's going to be 8 divided by the square root of n. And we are going to multiply that by our critical value that we just found. And let's see what that's going to give me. This is going to give me 2.0608. And then question C, let M represent the margin of error for this confidence interval. For what percentage of all samples will the confidence interval x bar plus or minus M cover the true population mean? And since we changed our confidence interval again, now we expect 99% of our samples to have confidence intervals that contain the actual population mean. Example 11. A machine used to fill beverage cans is supposed to put exactly 12 ounces of beverage in each can, but the actual amount varies randomly from can to can. The population standard deviation is sigma equals 0.05 ounce. A simple random sample of filled cans will have their volumes measured and the 95% confidence interval for the mean fill volume will be constructed. How many cans must be sampled for the margin of error to be equal to 0.01 ounces? All right, we are being asked how many. That means we are looking for the sample size. Okay, now we have a sample size formula because what happened was we took the margin of error formula and solved it for the sample size. And our formula is the sample size is going to be equal to our critical value which your book is calling it Z with the subscript alpha over 2, but in either case it comes off of table A3, okay, times the standard deviation, and then we're going to divide all this by our margin of error, and then we want to take this whole fraction here and raise it to the second power. Okay, so let's go find the pieces we need to find our sample size. Okay, the critical value, that's going to come out of table A3. So let's see, how confident do we want to be? Here we go, 95%. All right, in table A3, 95%, the critical value right above it, 1.960. The standard deviation given to me right here, 0.05. And the margin of error, this is what we're shooting for, 0.01. And now I have enough information, I can figure out what the sample size is. The sample size is equal to our critical value, 1.960, times sigma, our standard deviation, 0.05, divided by the margin of error, which we wanted to be 0.01, and then this whole fraction here, we want to raise that to the second power. All right, let's send the calculator and see what we get. Now when I put this in the calculator, this is going to give me 96.04. And what I did was I multiplied 1.96 times 0.05 and pushed enter. And then that I divided by 0.01 and pushed enter. And then I raised that to the second power. And it gave me this decimal right here, 96.04. We know this is a sample size, so our numbers should actually be whole numbers. And 96.04 is a decimal. And we are going to round this. But we are going to round up. And the reason we need to round up is because if we round down, we're not going to have the margin of error that we were hoping for of 0.01. So in order to preserve this, or make it as close to the 0.01 as possible, we're going to need to round up. So what happens if we round down? If we round this number down to 96, then our margin of error here is going to get higher. And we don't want to go higher than 0.01. We'd rather go lower. We'd rather have 0.01 or less than 0.01. So by rounding up every time, we can make sure that we have this margin of error or something smaller than that. So our sample size here, in this case, is going to need to be 97 cans. Example 12, an IQ test is designed to have scores that have a standard deviation of sigma equals 15. A simple random sample of students at a large university will be given the test in order to construct a 98% confidence interval for the mean IQ of all students at the university. How many students must be tested so that the margin of error will be equal to 3 points? So once again, we've got the question how many. That tells me that I'm going to be looking for my sample size. Okay, things we need. We are going to need to have a critical value. And let's see, I want to be 98% confident. So over in table A3, the critical value that goes with 98%, 2.326. The standard deviation given to me to be 15, and the margin of error we want to be equal to 3. Okay, I think I have enough information to get my sample size. All right, so plugging our numbers into our formula, we have 2.326 times 15. We're going to divide that by 3 and then square it. And in my calculator, this is giving me 135.2569. And remember, all of this right here, we want to round up. Even though the 2 doesn't round the 5 up, we want to round up anyway to ensure that our margin of error is 3 or less. So in this case, we want to have 136 in our sample. Okay, our last two examples deal with an interpretation of this 95% confidence interval. A scientist plans to construct a 95% confidence interval for the mean length of steel rods that are manufactured by a certain process. She will draw a simple random sample of rods and compute the confidence interval using the methods described in this section. She says the probability is 95% that the population mean length will be covered by the confidence interval. Is she right? Well, yes, this is a correct interpretation of the 95% confidence interval. It is true that the probability that a 95% confidence interval will cover the true mean is 0.95. Example 14. A scientist constructs a 95% confidence interval for the mean length in centimeters, and it turns out to be 25.1 is less than mu is less than 27.2. She says the probability is 95% that the population mean length is between 25.1 and 27.2 meters. Is she right? Well, in this case, no. And the reason she's not right is because she's already computed her confidence interval right here. So once we've computed the confidence interval, the probability doesn't exist any longer. Remember, the probability was measuring if we made several different confidence intervals, then we would expect for 95% of them to contain the true mean. But now that I have my confidence interval, I can't say there's a 95% probability that the mean's in there. It could be or it could not be. And it may be, one of the 95% that contains the true mean. We don't really know. But once you have made your confidence interval, you can't make any kind of a mention about probability any longer. She could have said instead that she's 95% confident that the actual population mean mu is between 25.1 and 27.2.